Welcome back, straight into the quantum realm. My name is Masha, and I hope you're ready to join me in this fascinating journey through the mysteries of quantum physics. In our previous episodes, we unraveled the mind bending concept of superposition, quantum entanglement, and quantum tunneling, exploring even deeper how particles behave in ways that challenge our everyday understanding. Now, it's the start of the most fun part there is, where all of those concepts fuse together into a beautiful and mysterious reality that scientists still struggle to explain. Today, we'll be exploring different interpretations of quantum physics that connects it to the world around us. This is episode 3, and it's the time when quantum physics really gets weird and even weirder. Quantum theory has a lot of different interpretations for its behavior in the science community. Those are different conceptual frameworks from different scientists throughout the field that connect all the known phenomena and its concepts in order to explain how quantum theory's mathematical aspects correspond to our experienced reality. But why do we need those interpretations? To start off, it is important to understand that quantum theory, like any other theory, is based on a series of assumptions, or postulates, meaning that the origin of each theory began with us assuming a certain aspect of it is true, or forming a hypothesis, and then exploring what that must mean. After which we perform an experiment and compare the predictions made by math to real life in order to test if one of the theories is a proper model for our universe. And if there is a match in between experiment and theory, there is a chance that the assumptions made in the beginning must be true as well. So far, the mathematical framework of quantum mechanics has been incredibly successful. But it doesn't always line up with our everyday experience. In other words, we have a bunch of experiments and results from them that perfectly line up with each other and contribute to our ability to actually use these concepts to our advantage. But the exact reason why those equations make sense remains unsolved these days. And since the interpretations are not theories that can be proven or disproven through a series of experiments, but rather a philosophical explanation for the obtained results, we can't actually choose a singular explanation for the entirety of the quantum world. At least, not yet. In fact, even after an entire century since the formation of quantum theory, physicists still remain sharply divided on the interpretations of quantum physics, since all of them make sense and line up with mathematical data, making it an issue of personal preference towards certain explanations. It's also possible for multiple interpretations to exist simultaneously, since each one of them takes its own approach to different postulates associated with quantum physics. Let's take a closer look at three of the most popular interpretations of quantum physics. First up, we have Copenhagen's interpretation, the most widely accepted view of quantum world. This interpretation states that the subatomic particles do not exist in singular state, but rather can be described as a wave function that we talked about in episode 1. And the features of this wave function accounts all the properties of quantum physics, like superposition, entanglement, quantum tunneling, decoherence, and all other phenomena that appears due to the wave nature of the particle, which is the successful explanation for the interference pattern in double-slit experiment. But this is also a place where problems start to occur, more specifically, the measurement problem. So, in Copenhagen's interpretation, pictures of wave function moving smoothly and predictably according to Schrodinger's equation until it hits a detector. And now, instead of a wave, we have a singular particle. This collapse of a wave function is the main reason for criticism that Copenhagen's interpretation is facing, as the interpretation doesn't clearly explain what a measurement is, why it causes the wave function to collapse from the superposition of possibilities to a singular outcome, or how this process occurs in the first place. It is also often seen as a pragmatic interpretation, making it philosophically unsatisfying for the majority of physicists. This approach discourages understanding an underlying reality and is widely known as shut up and calculate interpretation, since it provides the tools for predictions but does not explain the physical process of quantum phenomena. Next up, we have the many worlds interpretation, which does a way better job at actually accounting for the events that we experience in our world and offers the philosophical explanation for them. This interpretation began in 1957. Then Hugh Everett III proposed it in his doctoral thesis as a solution to the measurement problem. This interpretation takes the wave function to be physically real, suggesting that when there is a measurement of a particle in superposition, instead of a set particle collapsing into a singular state, it actually takes all of the possible states simultaneously, just in the different versions of reality. As you might already guessed, this is where the name of this interpretation comes from, suggesting that there are multiple alternative versions of our world that contain all of the possible outcomes that ever happened in the entirety of time our universe existed. For example, then the thing about the Schrodinger's cat, instead of a cat being both alive and dead until observed, the universe splits into two branches. One where the cat is alive, and one where it is dead. This is also the concept of the multiverse comes from, the theoretical concept that our universe is just one of many, possibly infinite universes. One of the reasons why I personally prefer this interpretation over the ours is due to the concept that stems from many worlds interpretation, known as quantum immortality. This concept proposes that when an individual dies in one universe, their consciousness could shift into a parallel universe where they survive in life threatening events, coming back to Schrodinger's cat. In this concept, instead of a cat, it's you inside of this box, and no matter how much time you spend there or how many times you might die, there will always be something to prevent your death, as your consciousness can exist only in the universe where you're, well, alive, meaning that technically we all are, in one way or another, immortal, at least from the first person perspective, since you will always be able to come out of the box in your new universe. But in parallel universe, there is a group of scientists that found your dead body. There is no real evidence to suggest that quantum immortality is true, but there is also no guarantee that it is entirely fake, since I never died, and I assume neither did you. But even with the inability to verify these concepts, there are still limits to this theory, as when if consciousness could continue to shift from one universe to another, it does not address the biological and physical process of aging, decaying, and diseasing. After a long travel through the universe, no matter the organism, all living things will inevitably die and be there without any cheat codes. But no matter how depressing this might sound for you, I find this concept extremely comforting, since you are guaranteed to survive and live a long life, but you still wouldn't live too long to make this life a burden. As I like to say, at one point, too much sequels kind of ruined the original movie. So let's make our lives worth dying, rather than not worth living at all. No matter how fascinating the many world interpretation is, and how much I personally want it to be true, it still faces a significant amount of criticism. One of the problems of it is the violation of Occam's razor. It is a problem solving principle that states the simpler explanation, or the one with the fewest assumptions, is often the best one. It's also known as the principle of parsimony. It suggests that when faced with a comparing explanation for the same phenomenon, you should prefer the one that requires the fewest number of new entities or suppositions. And in our case, many word interpretations might even be the most complex interpretations among the others, with its infinite number of unobserved universes and all possible outcomes inside of them. Another huge criticism that this interpretation faces is that many world interpretation kinda ruins the whole probabilistic property of quantum world. Since imagine if you got a particle that has 7% probability of being at one place and 30% probability of being at another place. And once this particle hits the detector, we have two universes, both of which have 100% probability of it being in one place and another 100 probability of it being at another place. So, if anything that could happen happens, what do those original probabilities even mean? This problem is actually addressed by another interpretation called cosmological interpretation, which says that many worlds theory is trivially true, but only the universe itself is infinitely big, since there's an infinite number of you doing the exact same action, and that infinite number of formed branches of reality kind of splits into the proportion of 30% of you that will see one thing and the other 70% of you to see the other. It's essential to note that while those interpretations provide intriguing insights, they still remain purely theoretical and untestable. But this is part of what makes quantum physics such a captivating field of study. The quest for understanding it continues, and each interpretation invites us to think about the nature of reality itself. As we wrap up this episode, we've explored why different interpretations of quantum physics are essential for making sense of the strange and mysterious reality we observe, from the Copenhagen's interpretation to many worlds interpretation. Each offers a unique lens through which we can view quantum phenomenon. I hope you enjoyed this episode, and make sure to stay tuned for our next and final episode, in which we'll be exploring how those concepts and phenomena can be applied in real life. Thank you for joining me on this journey. I can't wait to continue exploring the wonders of the universe with you. Until our next journey, right into the quantum realm.